Hello, everybody. Today's presentation is focused on our new battery module assembly using Technomatics Process Simulate and how it helps you to support battery smart manufacturing initiatives. Just a little bit about market trends. I mean, you all know that EV is basically in every market and growing in every market. These numbers are coming from Boston Consulting Group. And the current trend there is that there's a common focus that electrical vehicle sales will continue to increase dramatically over the next 5 to 10 years, changing the EV market share in the auto industry from meager positions in many of these markets to about 50% over the next years. So that, of course, increases the overall need for batteries, right? With a constantly growing need for larger capacities. And also, of course, lower cost, right? And therefore continue to be one of the biggest challenges for the automotive industry and also for battery manufacturers. So in short, that means for battery manufacturing that it's a real challenge and endeavor, right? Whether you are a current battery producer, a line builder, or even an OEM entering the market, right, with decades of automotive experience. So the question is, how will you manufacture battery cells, modules, or packs that meet demand, delivery, and quality targets, while also ensuring, of course, the safety, profitability, and also sustainability, and of course, a market-leading position. So if we look at, let's say, today's traditional approach to manufacturing and also line building, we see that starting from the planning phase, what you normally do, you hand the data over to the mechanical department. Then at the subsequent level, you hand that over to robotics and also electrics and automation. And this is all sequential, right? So communication is normally done via email, Excel, and whatever, right? And really, these disciplines come together in the real-world commissioning, right? So you identify issues not upfront, but actually at the real-world commissioning at the customer. And of course, that can lead to an inability to deliver on time, right? And at speed, while the world is demanding actually faster time to market. And also a fast delivery of these, let's say, equipment pieces and lines. Also, there's a lack of flexibility, right? So when it comes to incorporating future technologies, right, while you are actually messing with the quality issues and also, let's say, the inability to deliver at speed, you can't really innovate, let's say, your approach. And scaling up is also an issue, right? We are with an escalating scrap rate, quality issues, and also, let's say, a higher than market energy consumption. So traditional manufacturing processes are not able to meet the new demands. So what is Siemens' answer to that? We at Siemens, as you know, believe that embracing digitalization to survive the present and thrive in the future is the answer to that. So how would an approach like that look in the future, right? So what we present you today, you've seen it probably already before, but for battery specifically, we want to basically bring the disciplines of mechanics, robotics, and automation closer together, right? We indicate that as a shift left, for example. So while you look at the traditional approach with sequential engineering disciplines and design disciplines, we'd really want to have, let's say, a parallel engineering there. And what we present you today is basically an approach for battery with simulation and virtual commissioning. And the outcome of that is also a digital twin, which allows you to actually do the commissioning further, right? Run more optimization upfront before you go to real-world commissioning at your customer, and launch earlier and optimize more before you actually enter the real world. So it's all about shifting left and, let's say, identifying issues and problems upfront and run iterations of that before you actually go into commissioning. So to demonstrate this, there's, let's say, different possibilities we want to show and benefits we want to show today with the usage of simulation. What we really want to do is this line in the middle you can see is something we created as a team. The line basically includes various stations taking pre-manufactured battery cells, right, and assemble them into battery modules. It includes not only robotics applications, but also machining applications and also quality inspection. So in the following slides and with the following examples, we'll deep dive into several typical challenges and also the possibilities and functionalities of using process simulator to address them during the battery assembly process. So with this, I'd like to hand over to Noam for the first example.
Yeah, thanks, Matthias. So in this video, we'll talk about path planning, which will be demonstrated here on the loading station. We can see here a robot loading cells from the first conveyor to the skid, and then continue into the cleaning machine. So the video will focus on creating robotic collision-free paths while using the specific robot controller and analyzing the trajectory of the robot's path. So we'll start by creating a simple pick and place operation by defining the pick and place locations. And we'll check the path we created, and we can see that we have detected collisions. So we'll zoom in to examine it a bit better. And the reason for these collisions is that the path is missing some via locations. So we'll solve this issue by adding a home location and approaching the part locations before and after the pick and the place. This will change the trajectory and easily help us avoid the collisions. So after creating the collision-free path, we can set every parameter, just like on the real robot, making the digital twin almost identical to the actual one on the production floor. We can change the zone, the acceleration, the speed, and also the configuration of the robot to make sure the robot will perform the operation the same way every run. So now we'll define the specific controller for the robot. This is an Eston robot, but Process Simulate supports all the controllers of the main vendors. This is useful for defining the configuration and the logic layer and the vendor's specific syntax, which later on makes it easier to deploy it on the shop floor. So now we'll create swept volume of the robot, which represents the space the robot travels through during the operation. We can use this to analyze the path, and for safety issues, like in this example, we'll measure the minimal distance between the robot and the safety fence, and we can check if it's up to our standards. So the main value points here are to design and validate the robot path earlier by planning in a virtual environment, optimizing cycle time, ensuring safety, and improving the station's layout at the start, and using the specific robot controller syntax to generate native robot code for further download to the robot on the shop floor. So moving on to offline programming, we'll demonstrate this on the housing station, where we can see the yellow Fanuc robot on the right that loads and unloads the housings from the turning table. We'll show in the video how to create and validate robot programs. We'll load the robot backup data, develop logic instructions, and verify them by debugging and simulation. So at the start, we can see that the robot doesn't have any data associated to it. So we'll start by easily uploading the robot's backup data. This will ensure that the robot's actual settings, programs, frames, and configurations will be reflected in the virtual environment, which will enable us for precise planning, troubleshooting, and optimization for the processes. And we can see that the data was all uploaded correctly. And we'll start adding the logic layer to the previously created robotic path. So after defining the specific robot controller, FANUC in this case, as we saw earlier, we'll add the logic command in the FANUC's native syntax. And this .ls file was also uploaded from the robot's backup data and allows us to save time and maintain consistency throughout the code. We'll continue by adding all the logic to each of the paths needed for this program. And now we will start editing the main program of the robot. It was also imported from the robot's backup data. The robot's main program originates from a standard template that serves as a framework for all operations. The template is customized and adjusted according to the specifications and requirements of the program. We can also add error messages to alert an event of invalid input. So now we'll do a dry run, and we'll force the robot program number to examine the call for all of the individual paths we created. And we can see that the robot behaves as we would expect. Now we'll intentionally insert an invalid program number to examine the behavior of the robot. We see that it stops and the following alert message pops up. So finally, we'll unforce the program number and allow the simulation to run automatically based on the signals and logic we've created. So the main value points here were to efficiently create and modify the logic layer of robotic programs, minimize errors by validating the programs virtually before deployment, and decrease downtime and costs related to on-site debugging. Moving on to the interlocking video, it will be represented by the two Western robots in the stacking station. The objective here is to prevent collision between the robots and optimize the station cycle time. So in this video, we'll analyze the interference area, raise potential areas that the robot could pass through simultaneously, and then create logic to ensure the interlock for the remaining area. So we'll start by creating the swept volumes for both of the robots. And we can see that process simulate recognized two interference zones. So we're going to try to solve this. We'll adjust the robot's motion to try to solve the interference. And now we will check if there have been any improvement. we can see we're left with only one interference zone. So we'll run the simulation to examine the behavior of the robots. And we can see that the two robots are still colliding. So it's necessary to add logic and signals to solve the issue. Also, we can use the interference query to guide us where to insert the commands for the interlock. And we can see that the comments are created automatically. We can create signals for the robot to help us solve the interlock. And Process Simulate allows us to use a soft PLC to validate the robot's program against the logic before the actual PLC is available. This enables us to validate the program logic earlier in the process and save time at the physical deployment. So as mentioned previously, the native vendor syntax are supported by Process Simulate, and we'll use it to insert the interlock command for both of the robots. We'll present the signals and run the simulation once again. And we can see here the robots are interlocked. We can see that the robot gets permission to enter the interference zone only after the other robots has left it. And the main value points here are to prevent safety risks and material damage by identifying interference and validating the robot's interlock, reduce expensive rework by designing and optimizing collision-free robotic paths early on, and accelerate the time to market by simulating the manufacturing process sequences.
So thank you, Noam. So what we saw now was really the simulation part of things, right? So we went through a path planning for the first robot in that line, did offline programming with that KUKA robot, and also did the interlocking part for the two Aston robots, right? Which is the simulation within Process Simulate, right? What we want to do now with the equipment validation example is really connect that to a PLC, right? So next step is a quite easy example. Once again, it's around the stacking station, but we're going to focus on that little turntable in the middle. A quite easy example. And the real challenge is here to connect the signals of that turntable and the logic we created inside of Process Simulate to a virtualized controller, a virtualized PLC, and really test these signals, right? So test the automation logic, test the simulation against the PLC model, and also test our HMI panel we created in TIA Portal, which is the Siemens HMI and also PLC development tool. So what we see next is basically the signals of that turntable, right? So it got inputs, so control signals, and also outputs, so feedback signals for that little turntable. So it's basically about turning it left and right. And what we see next, this is TIA Portal. So this is the program logic inside of the PLC, which we created for it, right? And what we do with it, we go online to a virtualized controller and really download it to it and connect it to our Process Simulate, right? To really test it upfront before we actually go into real world commissioning. We prepared a little HMI to it as well, so test that as well. So this is how, let's say, an operator would work as well. So you would go to manual mode and really test that if it goes forward and backward, in this case, home and forward. And home doesn't, or seems to be not working. So going back to the HMI to really debug that. Right. In this case, it's an issue in the HMI, a simple typo. You can go back, change that, right? So we have 2 times the forward signal, so that doesn't work. Go back and change it to home, rerun the same thing, as a fast iteration of that process. Of course, in this case with an easy example, but you can easily scale that up, right? So you can test again, goes to home, goes to forward. Of course, the sensor signals are coming as well. So you can really test and validate your control system before on-site commissioning. Of course, you reduce the risk of having errors and downtime on-site and at the physical environment, so the most costly portion of it, right? And also you can accelerate your testing, right? Because you can test an iteration here within seconds or let's say minutes. On-site, you would have to open the safety gate, you would have to reset and go back, check where the issue is, maybe run through cables and so on, right? So it's a matter of seconds here. In real world, it's going to be minutes and costly minutes. So now, last but not least, let's say a virtual commissioning showcase where we run the same line, which we saw here in automatic mode, right? The first example is around, let's say, a quality inspection. So what we do there is really go through the quality inspection. So we generate issues and see, or defective cells in our case, and see how the line would react to it, right? So we added, or are going to add, let's say, testing devices as well. So in this case, we simply inserted a button, right, to create defective cells. So that red cell has an issue, right, which we could detect with a visual inspection, but it's simply the line doesn't have it yet, right? So we see, okay, what is the system going to do with that cell, right? At some point, there's going to be an adhesive tape added to that cell. This is that little station you can see. And what happens after that, the cell is a different, let's say, piece, right? And we lose track of it, right? So it goes subsequently to our module and we detect it later, right? So the issue later. And of course, that is a problem. So what we're going to do is we're going to add visual inspection and also an RFID reader, and we run the same test. So once again, connected to our PLC. So what you see on the left-hand side is once again that HMI panel, and what we see here is basically the visual inspection finds an OK cell, and this would be, let's say, the data shown to it, right? And once a defective cell runs through it, you can see right away it's detected and moved out of the line into an inspection line, right? And that issue is gone. So an easy test once again. So the next thing we have here is a little safety gate example, right? So once again, it's around that stacking station. We move to automatic mode, let the system start or the line start. So it's fully connected to the PLC. So the PLC controls our simulation in this case. So you can see the cells running in, you can see the big cooker robot actually adding housing. And now we're going to open the safety gate like an operator would do it in the actual world, right? And you can see that the little Aston robot is still moving. Of course, that is a safety hazard. So in this case, we go back to our safety program. Once again, figure out, okay, it's an easy typo, right? We change that, download the revised program to our virtualized controller, so the virtualized PLC right away, and run the same iteration. And once again, recover the mode, open the safety gate once again. And in this case, the robots pause, right? On the right-hand side, you can see the HMI panel. And what we're going to do now, we're going to test the recover, right? So we close the door and reset the fault and see everything is running up, is up and running again. You can not only test, let's say, safety stuff like that or easy stuff, which we saw with the turntable, but also your alarm tagging and everything, right? So everything is possible. So really the main points for that, of course, is risk reduction through testing, right, and validating. Time efficiency, once again, this is something really, really quick, right? It's a comprehensive approach to ensure that the reliability, so the recover mode, safety, and also efficiency of the industrial automation system is actually state of the art. So this is what we have when it comes to the examples. I hope we could show a good portion of, let's say, that that simulation virtual commissioning approach really helps you to shift left, right? So test early, identify, let's say, issues upfront, avoid risk, and also, let's say, save costs, right, for your customers. So when you look at the battery manufacturer, that means, okay, you can really enable design for manufacturing and standardize, right? So just imagine that little turntable we tested, right? It works. You put it basically to a library for you, and you can even let's say improve your efficiency when it comes to the management of the suppliers, right? So you have tested devices, you have tested cells, and so on, and really can help let's say with that collaboration with your suppliers as well. And of course, it minimizes your production shutdown as well. When it comes to the line builders, of course, it's all about meeting deadlines and reduce on-site work, right? So, of course, both is really, really costly at the end. Not only costly when it comes to time on-site, but also, of course, when it comes to deadlines. And in addition to that, when you're under pressure and on-site commissioning, of course, if you have an issue and if you make an error, of course, that can also damage hardware like robots, right? And this is really expensive. So at the end, for the line builder and system integrators, it's also about increasing overturn rate and also a competitive advantage to run, let's say, simulations up front with Process Simulate in this case. Before I let you go, I have a little reference case as well. So we saw these Aston robots, which we integrated with one of the latest releases, actually, as one of our, let's say, OLP packages, right? But the challenge for Aston was to deliver production lines for batteries in a very competitive market environment. The solution for Aston was exactly what we just discussed during this webinar, right? So adopting simulation and virtual commissioning with the Technomatics Process Simulate, right? So at Aston, that led to an accelerated development in engineering and commissioning process for the production lines, and also a reduction of cost without the risk of facing, let's say, damaging expensive hardware like robots. I do have two testimonials as well from two of their managers. So the project director of digital business said, by leveraging Technomatics Process Simulate, we reduce commissioning time by 30% and overall cost by 20%, benefiting of our customers with shorter production periods and enhanced efficiency. And also the general manager of digital business said, using Technomatics Process Simulate propels us forward, shaping agile production lines that outpace competition. In this competitive industry, so the battery industry, innovation is not just a choice, it's our strategic advantage. I think this is really powerful, right? Having somebody said that overall cost is reduced by 20%, this is really a benefit, not only for them, but also, of course, when it comes to commissioning time for their customers. All right, that's what we have for you today.